we're going to look at the meaning of the curl of a vector field. And this is something that in Stewart and in most books is you just get this pretty big hairy formula with partial derivatives, and then you do some calculations, you learn some properties, and then eventually you connect it to big theorems. But you can actually motivate it in a rather different way. So this is related, this is a generalization of what can be called the scalar curl of f in 2D. The curl is the analog in 3D. So the scalar curl, we've got a vector field. Maybe it's kind of swirly, we're not really sure. And we'd like to get a sense of the local circulation, and really it's the local density of circulation at some point. And so what we do is we create a circle or square or something, any kind of systematic shape that's a loop around here, or whose boundary is a loop around here. And we look at the circulation per unit area, and we look at this. We look in the microscope, meaning we take the limit as the size of that goes to 0. And so we define this scalar curl to be the limit as a size parameter goes to 0. And let's say it's a square of side length h. And so circulation around the boundary of that square. So the square is the 2D object, and it has an area. The boundary is, of course, the line, the curve that we could do a line integral on, a circulation on, f dot dr. Okay, so that it turns out to not really depend on exactly what shape you take. If it's a square or a circle, you get the same thing. And a calculation turns out to give that it, in fact, is just dq dx minus dp dy if f is pi plus qj. Okay, so with that in mind, we're going to look at a 3D vector field. Now, it's harder to draw a great 3D picture, but suppose we have a vector field that we kind of notice it's kind of swirling around when we look at it in the usual way, that it tends to swirl around planes, the rotation. Oh, I shouldn't go so far down. Actually, that'll barely work. Okay. This is X down here. I just forgot the edge of my frame. It tends to swirl maybe in the plane of the paper here. So maybe it's like swirling around like this, seen face on, and swirling like this, but maybe it's not really coming out toward us or in. It's not really swirling around an axis, a y-axis or a z-axis, just to be definite. So maybe it's something like this, like a pinwheely type thing that's swirling around an axis that would be coming out of the board. Then we would detect that in exactly the same way as we do here. We would take a little square, and here's the thing, here's the new thing, is I need to tell you not only where the center of that square is, but also how it's oriented in space. It's going to detect different kinds of circulation depending on whether it's in the plane of the paper or coming out like this or coming out like this, if it's like a YZ plane or XZ or XY. And of course it could also be a slanted plane in any kind of orientation. And we know how to describe the orientation of a plane. We can describe that with a unit vector. So for example, the one I've drawn here, this is a little square in a plane whose normal vector is going in the x direction. Okay, and so we could imagine we're going to get many, many, many different possible answers. We could take a very similar thing to here. We could take the limit as h goes to 0 of 1 over the area of that square. It's still going to be a circulation per unit area, but I guess I should decorate it with like an n here for normal vector. The boundary of that particular square with size h with particular normal vector n. So in this case, it's kind of coming out like that, of f dot dr. Okay, so this would be sort of the curliness around the axis given by that unit vector. Now you might imagine a pretty complicated situation where that's going to be a very complicated function of the unit vector we take. And so it's going to be all kinds of different numbers depending on all the different directions. There's like a sphere's worth of unit vectors we could take. And the cool thing is that that's not true. That in fact the information here, there's really only 3 different ones that we would really have to measure. And so it turns out that, and this is the part that's really hard, it's pretty hard to sit down and do this. I've occasionally done it with classes. That if you take a square whose normal vector is exactly in the x direction out of the page, and one that's exactly along the y direction, and one that's exactly along the z direction, and just give me those 3 numbers, that's enough information to determine all of these guys. So that's the thing you're going to need to take on faith, because I don't think we're going to do that in detail. And so here's the big fact, is that if I've got like the curl around of the vector field around an axis parallel to the x-axis, so this will be a temporary notation. Say with that, we discovered that's 7. So we did this exact calculation with the normal vector being I. Maybe I'll call it I, the I curl. Okay, and then the curl J is like -9, and the curl K F equals 3. Then if I did actually care about the curliness, the local circulation around some slanted plane with a weird normal vector, then the curl around that funky normal vector, let's say that's ABC, it turns out to just be 7A minus 9B plus 3C. In other words, it's the dot product with a vector made out of these 3 pieces of information. Now, I haven't told you any slick formulas for these guys, but we're going to see that that's going to be really easy based on what we know about the scalar curl. So in other words, it's just n dotted with, you know what? It makes a whole lot of sense when I have 3 numbers that specify what's going on with the vector field. They're associated to the ijk directions, and then when I have introduced, when they interact with another vector, they're exactly like dotting with a vector. Well, I'm just going to call that the curl of F. Okay, so that's a way to define the curl. It's a vector whose I component is the answer you're going to get if you do this with normal vector I, and whose J component is if you do this with normal vector J, so that's kind of coming out, down, back, up, and the K component is what you get when you do it with a horizontal plane parallel to the XY plane. Okay, and so this is the really cool thing, is that yes, there's one vector whose dot with any normal vector, any unit vector, gives me the curliness that I would care about in lots of different applications around these little different squares. And let's see. So let's look at curl K, for example. Curl K. Okay. Well, if you believe what I just said, okay, or if we go back to just what I proposed as what curl K would be, curl K should look awfully familiar. It's the limit as the size goes to 0, 1 over. So I create a square with normal vector K. I take 1 over the area and I integrate over the boundary. Okay, so that's something that's in a horizontal plane, so that's supposed to be horizontal. That's exactly what I'm going to get if I just take that plane, pretend it's R2, take that point in R2, ignore any K component, because remember, if I'm going to integrate over this loop, the dots are going to completely kill any K component. So basically pretend that my 3D vector field just lives in R2 by killing the K component and fixing Z to be whatever the Z value is here. And then doing exactly the scalar curl. So this is the scalar curl of sort of the 2D version of f, and we know how to calculate that. That was dq dx minus dp dy. Okay, the 2D version of f, the q and the p of that are exactly the same functions, except they might have a z in them, but I'm taking partial x and partial y anyway. Doesn't matter. Does not matter. Okay, and so that's going to be, this is going to be the k component of the curl, this full curl vector. Okay, that should look familiar. When you see the vector, the formula for the curl of a vector field in Stewart, this is the k component. You might have recognized, hey, that's something we were doing before. And then more generally, or the other two cases are really, really similar. If I look at vector field and I do, if that's z and y and x as usual, if I do one that is actually in the plane of the board, or the paper here, in a yz plane, that scalar curl is going to be what I get if I just look at the y and z components. So remember, in 3 variables, we usually use r for the k component, just for another letter. And so we're going to get let's see, for this one, it's going to be, want to make sure I get the right one. I'm not looking at the book. It's easy to get the signs wrong, and I was going to mention that in a second in terms of the orientation. And so that's going to be, I always have to work it out. This is yz, and so that's going to be dr dy minus dq dz. I'm pretty sure. You can correct me if I'm wrong on that sign. And that should be the x component, or the I component of the curl. Let's see. Yes, that's right. Okay. And then similarly, we get the third component of the j component of the curl from the other two partial derivatives, which come from treating this as a 2D problem and basically looking at the scalar curl. So the upshot of this is that yes, curl f does have a derivative formula, and the pattern we're getting of these combinations of partial derivatives and components is conveniently, and it's not at all an accident, but it's kind of deep that it's related to determinants. It has this wonderful mnemonic formula as if it's a determinant with I, j, and k unit vectors in one row, that's funky, functions in the bottom row, and derivative operators in the middle. This is a very funky thing to do, to take a determinant with each row being a totally different kind of object, and nothing's actually a number. It's very sophisticated. Okay. But from my point of view, this is a wonderful, it's not trivial and it's deep that this works, but it's not for me the real deep meaning of the curl, which is that the curl f dot any unit vector is a local density of circulation. That's going to be crucial when we use curl in its big theorem, which is Stokes theorem. So I really want to have that as part of our story.